Thank you for the introduction. I'd like to thank the organizers for organizing the conference and obviously giving me the opportunity to tell you about my work. So, like was mentioned, this is the last talk of the day, and if you're looking at the title, you're looking at the abstract, maybe it seems pretty far from what you usually do. So I'm going to spend most of the time motivating what I'm trying to do, and I'm going to try and provide as much background as possible. If you're a masochist and really want to see the details, that's where you can find them, or you can talk to me after the talk. So before I do that, though, I want to sort of give you a high-level introduction to the overarching theme of the talk. Hopefully you get your attention. So I thought of an introduction that recently got my attention, and this was the introduction to the UC cybersecurity training that I saw. This is mandated of all UC employees. And the title of the introduction was Think in Threes. So this is taken word for word from the slide. The number 3 surrounds us. 3 is the first recognizable and easy to remember sequence of numbers. The 3-act structure is the predominant model used in screenwriting, and a triangle is the strongest physical shape. That is why we rely on 3 security triads to lay the foundation of what it means to be secure. So I thought that definitely got my attention. So hopefully it works. And just to drive home the point, they even had a picture. So this was on the first slide. It's a picture of a triangle, in case you haven't seen one before. So credit to the security awareness company. Don't want to take credit for them. But I thought, I should also have a triangle to sort of drive home this point. But for our talk, the talk will be focusing on combinatorics, random matrices, and free probability. So that's sort of the triad that I'm thinking about. And the connections between these 3 are actually quite well established. So combinatorics and random matrix theory, combinatorics and free probability and random matrices. Right? So again, this is a well-established structure. The idea is I'm going to review the models for which this sort of triangle holds, which is well known, and then I'm going to introduce another model that's well studied, not well studied, but it's very interesting that we're trying to study, and we'll see how much of this triangle structure we can still get out of it. Okay, so that's the idea. So let's start from something that we do know about, random matrices. So this is sort of the basic picture. So you're considering a random matrix. For the purposes of this talk, I'm only going to consider self-adjoint matrices. So the reason why I want to do this is because then the eigenvalues are real, and I have very strong control on them using various techniques. So the notation that I have in this talk will be lambda 1 is the largest eigenvalue, and they go down. Sometimes you see this in reverse in the literature. But for me, lambda 1 will be the largest eigenvalue. From there, you can consider your spectral measure. So this is just the measure that places equal mass on each of the eigenvalues. And then you normalize to get a probability measure, because we're trying to do some probability here. And of course, since we're talking about random matrices, you now get a random probability measure. So the first natural question to ask is, well, if you start making your dimension larger and larger, what happens to the spectral measure? Well, in some sense, that's the second question to ask, because your first question should be, well, what kind of random matrix am I thinking about? So the first random matrix that you can think about are what are known as Wigner matrices. So the easiest model that you can think of is, what if every entry of your matrix is IID? But of course, you can't have this because you assumed your matrix was self-adjoint. So you're going to have this IID assumption up to the symmetry condition. So I'm going to tell you the distributions of the strictly upper triangular entries, the diagonal entries, and then from there we're just going to reflect to get the rest of the matrix. I'm assuming that my upper triangular entries are IID centered and of unit variance, possibly complex valued, and then my diagonal entries are going to be finite variance and real valued. From there, I'm going to get a self-adjoint matrix just as soon as I tell you what the upper triangular entries are. And by reflecting, I get what's known as a Wigner matrix. However, I'm going to separate 2 special cases. So if my strictly upper triangular entries were actually real variables, when I do the reflection, this thing's just real symmetric. And I want to distinguish this with what's known as beta equals 1. So a real Wigner matrix has this parameter beta equals 1. And if there were complex random variables, then when I reflect, I not just take the reflection, I have to take the adjoint, right? So I have to take the complex conjugate. So I'm going to call that beta equals 2. And in this case here, the first result is quite old. This is from the 50s. What happens to the spectral measure when you take n to get larger and larger? Well, it just converges to the semicircle distribution. Okay, so this convergence happens weakly almost surely, and it wouldn't be a random matrix theory talk if you didn't see a picture of the semicircle distribution. So apologies to those of you who've seen this for the umpteenth time. But if you have a matrix and you say the entries are taking plus and minus 1 with equal probability, then for n equals 5,000, I've taken a simulation of the eigenvalues. Those are plotted in blue, and the density that I'm claiming that it converges to, or Wigner proved that it converges to, is in red, and you'll see that there's very close agreement. And what you'll also notice in this theorem is that I'm not making any assumptions on the distributions of the entries besides that fact about the variances and centering. So this should still be true if I change the distributions of the entries. So let's make them Gaussian now. So this is what's known as the GUE. This will show up again, so that's why I'm sort of giving you the definition now. On the diagonal, I now have real Gaussians, 0, 1, and on the upper triangulars, I have complex Gaussians, 0, 1. And what you'll notice is that, well, it looks like the bars didn't even move at all. But just to convince you that I'm not cheating, they did move a bit. But of course, the limit should still be the same. It's still going to be your semicircle distribution. Another thing I want to convince you of, I didn't cheat here. There are no outlying eigenvalues when I do this simulation. So this result here says that your aggregate distribution, your spectral measure, converges to the semicircle distribution. It doesn't tell you what's happening with these extreme eigenvalues, though, right? You can technically still get convergence to something like this and have the largest eigenvalue be wandering off to infinity. And now in your simulation, you see that this isn't happening. So then the question becomes, is this actually the case? Do you get convergence to the edge of the spectrum, right? What is the spectral norm of your random matrix? And this is an old question.
Quick question before. Do you assume any relationship between the law of the diagonal entries and the off-diagonal entries?
No. So I just need the diagonal entries to be finite variance. Then they're independent. They're all independent up to the symmetry constraint.
Just take all the off-diagonal entries to be 0, for example.
Well, they have to have unit variance.
Oh, unit variance.
Right, so this rules out the triviality of, you can take your diagonal entries to be a 0 variance if you want, though, in the assumptions that I had. But most of what's happening is off-diagonal, basically. The idea is, but most of what's driving this is going to be in the off-diagonal entries. Okay? So then the question is, what is happening to the largest eigenvalue? And this is an old question. This is first studied by Frutti and Komlosch, and then the version that's definitively proven here by Bai and Yin says that the largest eigenvalue will go to 2. It'll go to the edge with probability 1, if and only if, this is a strong condition, your fourth moment of your upper triangular entry, that's what's driving all of this basically, is finite. Okay, so that's a nice result. Now that you have this location result, you can ask about the fluctuations of your largest eigenvalue. So what's happening around the limit? So this is much later. This is a seminal result of Tracy and Whittam for the GUE. They proved it later for the GOE and the symplectic ensembles. Soshnikov extended it to general Wigner matrices satisfying certain moment conditions, and the definitive version that I've written here is due to Li and Yin. It basically says that your fluctuations are converging to something known as the Tracy-Whittam distribution if and only if it has tails going to 0 quickly enough. Okay, so this limit distribution is not universal in the sense that it does depend on the symmetry class, but up to the symmetry class, it is universal. So there's one for all the real symmetric matrices, and there's one for all the complex remission random matrices. Okay, and just to convince you of our triangle from before, here's a connection to combinatorics. If you study the distribution of the longest increasing subsequence of a permutation chosen uniformly at random from the symmetric group, the fluctuations converge to the Tracy-Whittam distribution for GUE. And in fact, if you think about, so when I first saw this result, I thought, well, what about F1? If you actually consider the same question, but for random involutions, so permutations that are equal to their own inverse, then this thing will converge to the GUE Tracy-Whittam. All right, so these are some known results about fluctuations. How do you prove things like this? So one very robust technique that shows up again and again is something known as the method of moments. And the idea there is you're going to look at a trace in a power of your matrix. So your matrix is self-adjoint, so when you do that, the resulting trace is just the pth power of your eigenvalues. And this pth power of your eigenvalues, when you normalize exactly, is the pth moment of your spectral distribution, right? So if you want to study this spectral distribution, it reduces to studying traces and powers of your matrix. And this is very nice because there's a very simple program to sort of make this all work. For example, if you're trying to prove the semicircle distribution, what you would need to do is just prove that the moments converge to the moments of the semicircle distribution, prove that the variances are sufficiently decaying, and then you get that the result is going to be the semicircle distribution. In particular, the moments of the semicircle distribution are given by the Catalan numbers. So again, you see the ubiquity of the Catalan numbers. This actually works for a lot more than just the spectral distribution, though. So you can use this method of moments. You need to do it with very fine control. You need to be able to do this with p increasing as a function of n. But you can use this to study things like the previous slide. So Soshnikov used the method of moments to extend Tracy-Whittam to general Wigner matrices exactly by understanding how these moments grow with p as a function of n. So it looks kind of like, well, okay, this is a very simple technique, but you can use it to study quite complicated things. Okay, so all these are nice results, but this isn't actually what Wigner was interested in when he first introduced this model. So when Wigner first introduced this model, he was interested in this idea of universality at a local scale. So what you've seen is universality at sort of a global scale. For example, the fact that the semicircle law holds regardless of the distributions of the entries up to the modest assumptions. But what Wigner was thinking was that the spacing of the eigenvalues, the distribution of the gaps between the eigenvalues, should actually be modeling the distribution of the energy levels for heavy nuclei atoms. And based on his observation that the spacing in the nuclei atoms were universal, he thought, well, then the random matrices should exhibit this behavior as well. So how do you actually prove something like this? This is a program that's now been achieved. And the idea is you first do it for these very nice ensembles, these invariant ensembles or these integrable ensembles. So the GUE or the GOE. And the reason why you want to do it there is because of this algebraic structure, you can actually write down explicit formulas for many of these objects. For example, you can actually write down the explicit joint density of the eigenvalues for the GUE and the GOE. They involve things like van der Maan determinants. And then from there, the idea is, well, you're just going to do it by comparison. And we're just here is not really doing it justice in the sense that it's very difficult. But this is now done due to a lot of work. Groups like Erdish and Yao and their co-authors, and also Tao and Vu. So what they prove, what's known as eigenvalue universality. So the spacing doesn't depend on the distribution of the entries. And they also prove something known as eigenvector universality. So in particular, the eigenvectors are delocalized. So what does delocalization mean? Delocalization, at least for the purposes of this talk, I'm going to consider very special cases of it. So you consider the eigenvectors associated to your eigenvalues, and the idea is whether or not the mass of your eigenvector is carried only on a few coordinates, right? That would mean localized. So for example, if your eigenvector was something like a standard basis vector, that would be localized. All of the mass is stuck just on one coordinate. The other case is delocalization. I'm taking this guy to be sort of the characteristic delocalization vector. So in some sense, this is the most even you could possibly have it, right? Every coordinate has the exact same mass. And what they've proven is that eigenvector universality holds. Typically, your eigenvectors are delocalized. And there's actually a way to quantify this by basically saying, well, how far does it deviate from what you expect an eigenvector to be delocalized by? So now that we've accomplished this program, what else? Well, now that they've accomplished this program, what else is there to do? So here's a picture. You guys will have to resist the urge to think of this as a Young diagram. That's not what I'm trying to do here. So this is what's called beyond mean field models. So if you think of your matrix as empty beforehand and you fill it up with entries according to your Wigner model, well, what have you done? In some sense, you've just filled it in black completely. Everything's more or less the same, right? Everything has the same variance. Everything's sort of surviving and it can interact with each other. Well, that's not very realistic when you think of it from a physical perspective. So from a physical perspective, you imagine situations like short-range interactions, right? So this is sort of characteristic of random Schrodinger operators. So in a random Schrodinger operator, you have IID potentials on the diagonal, and you only have nearest neighbor interaction, right? So you only have the nearest site that you could possibly interact with. And the question is, well, what is the behavior there? And it's sort of a well-known result that you get localization and Poisson statistics. So you get localization for the eigenvectors, and the distribution of the gaps between your eigenvalues look more like Poisson, which is sort of like independence. Whereas in the case of random matrices, you get these van der Maan determinants, you get repulsion, so there isn't really any independence. There's a weak correlation, right? So then the question is, well, what about something in between? You've got this guy over here on the left where you only have just the diagonal and the super and the subdiagonal. You have this guy over here on the right, which is basically just all filled up with black. Can we interpolate? And that's sort of where we get the motivation for our model. This is what's called the random band matrix. You're doing exactly what you did before. You have entries to fill up your matrix with. However, you're only going to fill them in if the entries are within a certain distance of the diagonal. And this Bn is your bandwidth. It is going to be measuring the distance at which things survive. Okay? So here's the formula for it. I'll show you a picture in a second that'll make it very clear. The only difference really is that you're only doing this if the I and j are close together, and your normalization is different now. So the normalization that we had before was square root of n, because that's how many entries were in a given row that survive, right? There are n entries in a given row that survive. If you think about what's happening in this picture, you'll see that in a given row, typically you'll have 2 bn plus 1 entries that are surviving. So this normalization is just to make everything sort of fit nicely in the end. You'll get variance 1. Okay, so again, this is our definition of a random band matrix, and if you want to understand what's happening here, the idea is you think of your random Schrodinger operator, you think of your Wigner matrix, and you imagine they had a child, right? So if they had a child, this matrix would probably look something like this, and this is our random band matrix. And this isn't actually going to be what I'm working with, because I want to work with a little more structure that makes things nice for me. I'm going to work with something called a periodic random band matrix. The reason for this will be pretty clear as soon as I show you this picture. So imagine this red submatrix that's sitting inside of your band matrix. And imagine you move this submatrix down across the bandwidth. What happens as soon as I break past? Well, in the left-hand side, in the regular band matrix case, the picture breaks down, right? But in my periodic case, when I've reflected the bandwidth condition across the boundary, this picture still survives in some sense. I still have my submatrix pulling through all the way. So this is a nice condition to have, because even though this model still isn't mean field, in some sense, at each location, the picture looks the same. So it's homogeneous in some sense. And if you really want a formula, there's the formula for the bandwidth condition in the periodic case. All right, so now that we have our model, and now that we have the motivation, we can ask the same questions that we had from before. What about the global behavior? So it turns out this thing is still semicircular as soon as your bandwidth is increasing fast enough, basically just as long as the bandwidth goes to infinity. What about the fluctuations of the largest eigenvalue? Well, if your entries are sub-Gaussian, so this is a result due to Soden and then Bandera and Van Handel. If your entries are sub-Gaussian, then your largest eigenvalue will go to 2 with probability 1, if and only if your bandwidth is growing faster than log n. In some sense, you need enough randomness to make this happen. If you don't have enough entries, then the effect of a few entries is sort of strong enough to pull things off what they should go to. And in fact, you even have Tracy-Whittem, but you only have Tracy-Whittem, so the second part is only due to Soden. You only have Tracy-Whittem if your bandwidth is growing faster than n to the 5/6. Okay? Now, the remaining question is this universality business, and that's actually sort of the hot topic. So there's a conjecture due to a number of physicists that there should be a transition in the local statistics and the eigenvector behavior around this critical rate, square root of n. So if your bandwidth is growing slower than square root of n, it's so small that I guess it looks like a Schrodinger operator, so it should exhibit plus on local statistics and eigenvector localization, like the Schrodinger model. Whereas if it's growing fast enough, faster than the square root of n, then it jumps over, and now it's like the random matrix theory side of things, and you get eigenvector delocalization, right? So a number of articles from the physicists, I think 4 out of 5 of these are in physical review letters. So very interesting from the physical side. And what's the progress on this problem? So eigenvector localization was proven for bandwidth slower than n to the 1/8 by Schenker in 2009. This is upgraded to n to the 1/7 by Peled, Schenker, Seamus, and Soden in 2017. Delocalization was proven for bandwidth faster than n to the 6/7. This is Erdish and Knowles. This is upgraded to 4/5 by Erdish, Knowles, Yao, and Yin. And then in a recent paper by Bourgade, Yao, and Yin, this is now n to the 3/4 plus alpha for any alpha bigger than 0. They actually prove something much stronger than eigenvector delocalization, which I want to emphasize here. It's quantum unique ergodicity. It's this idea of somehow being uniformly delocalized. So in some sense, in every coordinates that you look at, so I don't really want to write down an equation because so say that psi is one of your eigenvectors, and I is just some subset of the numbers 1 through n, then if this thing were extremely localized, then the sum of the masses in those coordinates should be pretty close to just the number of coordinates divided by n, right? Instead of just the whole thing, you can look at any small picture, and this should be the case. So what they've proven is that there's a uniform bound on something like this. I forget exactly the constant. I'll say something like that for any of the eigenvectors at the same time. So this is a uniform control on the eigenvectors uniformly and sort of where you look at the eigenvectors. So this is an extremely strong result. You'll notice that I've only mentioned eigenvectors down here, even though the conjecture is about local statistics. So the question is why? And the answer is, well, localization implies Poisson statistics. This is a result due to Minami. And quantum unique ergodicity will imply random matrix theory local statistics. So if you can prove quantum unique ergodicity, then you're pretty happy. You'll get the other half of this conjecture. Okay, so the whole point of this is that this question is very interesting as physical motivation, and if you're not working in one of these groups, it's probably a bad question for you to be working on. Okay, so these guys are sort of just taking over by storm, right? So what I'm going to do is I'm going to take this model, random band matrices, I'm going to take this exponent, n to the 1/2, and I'm going to look somewhere else, hopefully to find interesting behavior. Okay, so where I'm going to look is in a field called free probability. So what is free probability? This is probably something that not too many of you are familiar with, but here's the definition, and here are some examples, and I'll explain it as we go through. The idea is you work in some algebraic version of probability. You have your algebra, which you're thinking of consisting of random variables, and you have a functional that you're thinking of as acting as an expectation. Okay, so the simplest example of this is, of course, just usual random variables. You have an algebra of random variables, and you have your expectation. You can also consider matrices. So you have matrices, they're non-commutative, and then you have this expectation, which is now your normalized trace. You take the combination of those two examples, and of course you get random matrices, which is where we're focused on in this talk. And sort of the two classical examples from a historical point of view are just bounded operators on a Hilbert space with a vector state and a group algebra with the canonical von Neumann trace that just picks out the coefficient of the identity element. Okay, so these are just examples of such objects. Are there any questions about the definition of a star probability space? Great. So you can tee up the usual notion of independence in this framework pretty easily. So if you're thinking about random variables and they're independent, then one property that they have, assuming the expectation exists, is that the expectation of a product factors as the product of the expectations, right? So you can write that in this abstract framework in the following way. And of course, the usual random variables will satisfy this if they're independent. But also, if you consider your group algebra example from before, if your group actually decomposes it as a direct product, then these subalgebras will be classically independent in this situation here. And this example is sort of the motivation for free probability. So Voiculescu came up with, so free probability is a creation of a guy named Voiculescu. And the idea is, well, let's look at this relationship again. If I consider the elements as centered instead, then I can change the factorization property to just say that the expectation of the product will be equal to 0, right? Because then it would just be the product of the expectations, but each expectation is 0, so that's just a product of a bunch of zeros. Well, if instead of assuming everything's independent, what if we work with something where things aren't independent? So here's the definition of free independence. We'll take a look at it for a few seconds, and I'll explain how this is showing up. So now I'm only assuming that the elements are coming from consecutively distinct algebras. I'm still assuming that they're centered, but now the trace on that product is going to be equal to 0. So where does this actually show up? So this is the second bullet point, but this is sort of historically the first example. If you have subalgebras of your group algebra where these groups are actually giving you a free product, then these subalgebras will be freely independent. Okay? And the connection to random matrices came in '91 in a paper of Voiculescu when he proved that unitarily invariant random matrix ensembles are freely independent in the large n limit. So if you want to understand how traces of words in your random matrices are behaving for large n, well, you just need freeness to compute that. And then Dykema extended this to general Wigner matrices, which I'm sort of using the umbrella term of mean field matrix to describe. Okay, so the operation that I really care about today is free convolution. So the idea is if you know the distribution of two random variables and you know that they're freely independent, in analogy with the usual case, when you take their sum, you now know the distribution of the resulting object. That formula that I gave you before allows you to decompose, and you can get all the moments just from the marginal distributions, right? So that's the observation that I've written down here. The question is then, well, if I have this definition, how can I actually compute such a thing? So given two probability measures on the real line, I can define their free convolution exactly as I described. You let x have distribution mu, you let y have distribution nu, you assume that they're freely independent. The free convolution is defined as the distribution of the sum, that random variable that has the sum. How do you actually compute this thing in practice? Well, this is a result of Bercovici and Voiculescu. So you take your Cauchy transforms of your measures, you take their reciprocals, and then you take their compositional inverses. And it turns out that the free convolution, the thing that you want, satisfies this identity. Okay, so you can compute this just using the Cauchy transforms of each of your marginal distributions. And to convince you that you can actually do this, I did an example. So here's an example motivated from random matrix theory. I have a Wigner matrix. It's converging to the semicircle distribution. I have a diagonal matrix where I assume that on the diagonal I just have plus minus 1 with equal probability. The result of Voiculescu and Dykema shows that these two things will be freely independent. So the spectral distribution in the limit of my sum will just be given by this free convolution. All right? If you do the calculation I showed you on the previous slide about inverting these transforms, you will get something that has density given by the formula below. This is just a horrible formula. I want to show you a picture to show you that free independence is really different from classical independence. So this is our semicircle distribution. And say that we took a classical convolution with plus 1 minus 1. So what would happen if I took a classical convolution with +1, -1? I'd have the two copies of it. One would get shifted over by 1, and the other guy would get shifted over by -1, so then the middle would sort of bump up, right? So in our picture, that looks something like that guy. So that would be the classical convolution of a semicircle distribution with +1, -1. That density that I wrote for you on the previous slide splits into something that looks like the McDonald's logo. So it just takes your circle and it puts it down into the center. Okay, so free independence is really a different object. Great, so what we're going to use it to try and study are finite rank perturbations. So this is a result that's increasingly general, but the result I'm stating here really I think can be found already just in this paper here. So let Wm be a Wigner matrix and consider a localized perturbation. So what do I mean by a localized perturbation? I'm adding here a matrix unit. This is just a matrix that only has 1 in the 1-month coordinate. It has zeros everywhere else. Its only non-trivial eigenvector is E1, which is localized. That's why I'm calling this a localized perturbation. And the eigenvalue that it's coming with will be theta. So I'm controlling theta. Theta is free to be whatever it wants. If I make theta large enough, it turns out when I add this guy to my Wigner matrix, then the largest eigenvalue will go to theta plus theta inverse, right? So when theta is small, when theta is less than or equal to 1, the largest eigenvalue will still go to 2. But as soon as the intensity of your perturbation is large enough, it'll pull the top eigenvalue out of the semicircle beyond 2. Okay, so that's the result that's being stated here. Furthermore, the fluctuation of that largest eigenvalue will change. All right, so there are some things that I need to explain on this slide here. But first of all, what you should notice is that the scale of the fluctuation changes. So the usual scale of the fluctuation was n to the 2/3 for Tracy-Whittam. Here, the scale of the fluctuations is now square root of n. And the distribution of your fluctuations will be this convolution, where this is a normal distribution, and the variance is given by this formula here. So this beta is coming back again, depending on whether or not your thing is real symmetric or complex remission. And I need to know the fourth cumulant of one of my matrix entries. Okay, so this is a highly non-universal result. The result actually depends on the particular distribution of your matrix entries. On the other hand, you can consider a different type of perturbation. So instead of considering a localized perturbation, you could also consider a delocalized perturbation. So what's the corresponding result for that? Well, here's a delocalized perturbation. Jn is the matrix of all 1s. Okay? I'm scaling it by n, so that its eigenvalue will now be 1, and then I'm multiplying by theta, so its eigenvalue will now be theta. The non-trivial eigenvector associated to that matrix is this bottom guy, the eigenvector, the vector of all 1 over n's. So, in this case here, my largest eigenvalue exhibits the same behavior. However, the distribution, the limiting fluctuations, the distribution of the fluctuations are different. It'll now become universal. It only depends on the symmetry class. Okay, so we'll have an explanation for this later, but I prefer to explain it all at once. Are there any questions about what this result is stating? So we used to have a semicircle going to the edge. We throw in this rank 1, not even finite rank 1 perturbation, and depending on how strong the eigenvalue of that perturbation is, you might get behavior pulling it out. Okay? So what do I see here? I see a sum, and we just discussed free convolution, so naively, you might think, why don't we just try and use free convolution to do that, right? So here's the attempt at this. You have your Wigner matrix. It's going to the semicircle distribution. You have your matrix unit. It's going to the Dirac mass, because there's only one non-trivial eigenvalue. So if you take your convolution, free convolution, you would just get the semicircle distribution, right? So nothing's changed in some sense. So that was a lot of work for nothing. But I didn't put on a tie today, just to stop there. So here's our second observation. This is due to a number of people. I just decided to give them all credit just to make everyone happy. So this is Berkovici, Belinsky, Capitan, Donati, Martin, Ferral, and Fevrier. So let's remember what we needed to calculate the free convolution. We needed the Cauchy transform. The Cauchy transform of the semicircle distribution is this function here. What's the reciprocal of that function? That's pretty easy. What's the compositional inverse of that function? It's z plus z inverse. Why does that look familiar? Well, that looks a lot like theta plus theta inverse, right? So this free convolution calculation, though it failed spectacularly here, in some sense you expect that there should be something happening that allows you to use this framework still. Okay, so that's where we get to infinitesimal free probability. This is a lot of reading, I know. So I'm going to let you take a look at it for a second. I'll tell you a joke in the meantime. So a mathematician dies and goes to heaven to be judged. And when she gets to the gates, St. Peter takes out a scale And on one side of the scale, he puts all of the mathematician's theorems. And on the other side of the scale, he puts all of the mathematician's definitions, right? So depending on the balance, there's your afterlife. So I've given you a lot of definitions for your sake and mine. Hopefully there's a payoff. So an infinitesimal probability space is this idea of your star probability space from before, where you're having an additional linear functional. So this linear functional, the notation is actually quite suggestive. It's supposed to be acting like a derivative. Okay, so this is why phi prime of 1 is equal to 0. So we're going to call something infinitesimally free if it satisfies freeness, first of all, and it satisfies this Leibniz-looking rule, right? So this looks kind of like a derivative, because this would be a product rule. This definition here maybe isn't so illuminating. What you should think of is this bottom definition, which is equivalent. So the idea is you take your functional phi, you add t phi prime to it, that gives you a new functional phi of t. You consider this expectation of these products where, again, they're alternating. If they were free, then since you've subtracted off the mean in each of these, you should be getting 0, right? That would be the definition of freeness. However, as a function of t going to 0, what you're going to claim is that this thing is bounded by O of t squared. Sorry, this is bounded by t squared, a function of t squared. But what does that mean? That means that the constant term is gone, and that means that the first order term, just the t term, is also gone. So in some sense, you get freeness to the 0th order and the first order. The term that's coming in is the second order term. So not only are you getting freeness at the top level, you're getting freeness at one level below. Okay, so that's why it's this notion of a derivative. Okay, so where might this show up? Well, you should expect that you might see this in the context of random matrices. So I've tried to tee this up as much like a derivative as I could. So you assume that a trace of any polynomial in your random matrices converges. At the finite stage, we'll call that functional phi of n. If you also assume that phi of np minus your limit exists, then this will be our new definition of phi prime. And this guy here looks a lot like a derivative if you let h be 1 over n. Because if you let h be 1 over n and you have this equality approximately, then it looks a lot like the formula for a derivative, right? So that would be your normal derivative. So the idea is, well, we need to compute some infinitesimal distributions then. So we actually want to compute what these guys are for some certain matrices so we can understand the 1 over n correction. So if you're thinking about this in terms of rate of convergence, basically we're asking whether or not there's a 1 over n term that we can pull out of this. Well, let's look at our Wigner matrices. So we know that in the limit, they converge to the Catalan numbers. This was just the statement of the semicircle distribution. So that's the result there. What we're asking for is whether or not you can multiply this by n and still get a finite limit, right? Whether or not there's a 1 over n term in your rate of convergence. And again, this is just because this is what we're looking for in our definition. And it turns out you can do this. So for the GUE, this is just a consequence of something known as the genus expansion. So in the GUE, what you have is that your rate of convergence is defined in terms of powers of n to the minus 2. So your first term will be your constant term. The next order term will be n to the minus 2. The next order term after that will be n to the minus 4. So if you just multiply by n, then your next term is n to the minus 1, and that just goes to 0 anyway, right? So you actually get nothing, and you get the null measure. So your infinitesimal distribution for the GUE is somewhat trivial. However, for the GOE, this already becomes different. So this is a result of Johansson from '98. If you do the same calculation for GOE, the resulting measure you get is a signed measure. Of course, it's a signed measure, and of course that the mass of your signed measure should be 0 because your phi prime of 1 is 0. And your signed measure is given as the difference between just a Bernoulli and the arcsine. Okay? So what can you do with this? Why are we sort of working so hard to compute these guys? Well, let's think about just the finite rank perturbation. So what is the infinitesimal distribution of a finite rank perturbation? For your finite rank perturbation, you don't actually have too many non-trivial eigenvalues. In particular, n minus 1 of your eigenvalues are 0, and you just have the one eigenvalue at theta. So this just pulls apart. You can add the 1 over here and subtract it off. And this would be your 1 over n correction, right? That's exactly what I've written down here. In the first term, I've written down the dominating term, and it's over here I've got my 1 over n correction. This is still true for the matrix of all ones suitably renormalized. Okay, and what Shliatenko proved was that if you have your GUE or GOE, then this matrix and the matrix units are asymptotically infinitesimally free. Now, the upshot of this is we can calculate something known as an infinitesimal free convolution. Okay, so not only can you understand the 0th order terms, you can understand the 1st order terms by combining your understanding of the individual 1st order terms. So here's the result that we had from before, just about regular convolution. The resulting free convolution distribution satisfies this identity. To actually make this work, we're going to use a different way to characterize the free convolution. It's using something called subordination functions. If you don't know what they are, that's fine. They just satisfy this identity. That's sort of the point. The infinitesimal framework says that we can also understand this 1 over n correction of our resulting sum. It's given by this functional identity. This looks a lot like chain rule, which is why, again, we think of derivatives. So if you have these individual marginals for your distributions, you combine them in this way. You now have the Cauchy transform for the 1 over n correction of your sum. You can invert that guy. And if you invert that guy, you get the 1 over n correction for your sum. So why is that useful? Well, here's a calculation that was done by Shliatenko. You take your semicircle distribution. That's the 0th order term, and your 1st order term, we agreed in the GUE case, was the null distribution. You take the infinitesimal free convolution with the 1 over n correction of your finite rank perturbation, and what do you get? As your 0th order term, you still get the semicircle distribution, so this is actually doing this calculation. I'm hiding this in the background. But your 1st order term is this difference, where this is a continuous distribution with support between -2 and 2, and you get a Dirac mass sticking out at theta plus theta inverse. So you're able to pick up on the outlier using this free convolution machinery in the next level. Just one step below, at the 1 over n correction, you can find your outlier in the form of a Dirac mass. Okay? And if you want to do this for GOE, you just have to add this guy to this distribution, but this is still fine because this is still supported between -2 and 2, so you're still able to see that there's this theta plus theta inverse sticking out. All right, so then the question becomes, well, can you do this for general Wigner matrices? And it turns out you can. To do this for general Wigner matrices, first of all, you need to know that a general Wigner matrix has an infinitesimal distribution, a 1 over n correction. So here's just a formula for that. This is the result of Enrique and Menard from 2016. So this thing is highly non-universal. There are a few things that I need to explain. The beta, you guys remember, depends on whether or not this thing is real symmetric or complex Hermitian. This s squared is the variance of a diagonal entry. It could be 0 now, so it didn't affect the limiting distribution, but it affects the next level, the 1 over n. And this alpha is the 4th moment of an entry on the strictly upper triangular portion of your matrix. Okay, so your 1 over n correction will be given by this guy. And what we showed was that your Wigner matrix, in this generality, is asymptotically infinitesimally free of the matrix units and the normalized all ones matrix. So this will be important later. Originally, we just knew that it was free of the matrix units. These are the matrices with only 1 in a single entry. But I also want to be able to compare this to the normalized all ones matrix in a second. Okay, so at this point, the very natural objection is that we've worked very hard for all of this, but in some sense, we've only just recovered results that are already known, right? This is still just the result of Pichet from 2006. So you might be thinking this guy's definitely going to hell, but I'm trying to convince you that, well, that may still be the case. So here's the idea that we had. So we're going to study free probability for random band matrices. Instead of looking for a transition at the level of just one matrix, we're going to look at multiple matrices. So free probability allows you to study multiple matrices at the same time. So the idea is, well, can we find anything that's happening at square root of n for multiple random band matrices? So this is just a reminder. For a single matrix, we still have convergence to the semicircle distribution. And what we showed earlier was that, well, free probability still works for random band matrices. You can sort of do everything that you would want to do in the usual case. For example, if you have independent random band matrices, they're still asymptotically free. So I think it's just best to sort of see this in a picture. So in the blue, I've plotted the eigenvalues of the anti-commutator of 2 independent Wigner matrices. In the red, I've plotted the eigenvalues of the anti-commutator of 2 random band matrices. And of course, you see very little of red and blue because it's mostly purple because they overlap, right? So the behavior of the pairs is very similar because freeness governs both of them, right? So again, just regular free probability, you're not seeing much because it just behaves as it normally would. In particular, the rate of the bandwidth does not play a role. You get freeness as long as the bandwidths are growing to infinity. They could be growing to infinity at different scales. One could be growing at n to the 3/4, the other could be growing at n to the 1/4. The two of them will still be asymptotically free. So then the idea is, well, we have this new machinery. We have infinitesimal freeness. Is there any way we can find some sort of transition for those guys at the level of infinitesimal freeness? And it turns out we can. So here's the result. This was our random band matrix, and to make things nice, I'm considering the matrix that I'm taking to be GUE, so it was GUE, and then we cut off all the Gaussian entries, but the entries that do survive are still Gaussian. So if I take the 1 over n expansion of my periodically banded GUE matrix, it breaks up into a few cases. So if the bandwidth is growing faster than the square root of n, it's going to be 0, which matches the usual calculation for the GUE. However, as soon as I dip below square root of n, it blows up, okay? And if I'm exactly on par with square root of n, say that the bandwidth divided by square root of n goes to some constant c, then I get some non-trivial value between 0 and infinity. It's written as a sum of a bunch of graphs. These graphs are the things that you saw on the very first slide, not the other triangle, but the colored triangle. And what we can show is that if you have independent copies of your random band matrix, then they're asymptotically free if and only if your bandwidths are faster than square root of n. Okay, so another thing that's interesting, and this is sort of the main thing that I'm working on now, is they're also asymptotically infinitesimally free from the matrix units and the normalized all ones matrix. So why is this sort of why is this an interesting result? Well, you can repeat the calculation that we had from before. So let's perturb our random band matrix. We have our random band matrix, and we add a finite rank perturbation to it, either the matrix unit or the all ones matrix. Well, all you need to compute that convolution are the individual distributions, right? And we just showed that this guy in this regime has the exact same infinitesimal distribution as the GUE. So when I compute this convolution, it behaves exactly the same as the GUE. In particular, I'm going to get an outlier at theta plus theta inverse again. The same is true if I add in the matrix of all ones. However, the situation here is very different from the Wigner case, right? So let's sort of see what I mean by that. But is the result clear, what I'm claiming? OK, so let's look at a picture of what's happening here. This was our random band matrix, right? And if I add just a localized perturbation, my matrix unit, this E11, then what have I done here? I basically just put a bomb in the first coordinate, right? So if you're playing Minesweeper, how do you play Minesweeper? You play it locally, right? So in some sense, dropping all of the perturbation in one coordinate only affects the coordinates around it. So when you do this trace expansion, it does seem quite reasonable that the behavior will resemble the usual Wigner case. You'll just basically do it in this little corner. And in fact, not only should it resemble the Wigner case, you can even have a guess as to the scale of the fluctuations. It should behave like a Wigner matrix, not of this full size, but only like a Wigner matrix of this size, right? And this is actually borne out in the simulations. So this is something that we can't prove yet. This is what we're working on now. So you have your matrix. You add the perturbation. You look at its largest eigenvalue, and you subtract off where you think it should be. And you scale by the usual scaling that you would expect from the result of Pichet. However, instead of 2bn plus 1, the usual result was square root of n, because that was the size of your matrix. In the picture that I showed you, we expect our matrix not to be square root of n size, but only the size of that red submatrix, which is on the scale of the bandwidth, square root of the bandwidth, according to our normalization. And if you do that, you get convergence in distribution. Well, you get a close matching in distribution to what you would expect. So in the normal case of just a GUE, the limit should be Gaussian. And what you see is that in blue, I've plotted it for bandwidth growing at the rate 3/5, and in red, I've plotted it at bandwidth growing at the rate 2/5. Again, you see mostly purple. The result is the simulation is somewhat surprising in the sense that it still seems to be holding for bandwidth growing slower than square root of n. This is somewhat bizarre because the result of Soden says that we should see a transition at n to the 5/6 for the largest eigenvalue. But when you perturb, somehow things get regularized and you don't have this issue anymore. It seems like it's still just going to be same behavior going through all the way down. This maybe is a bit hard to see, and you're not convinced that this, so this black line is the Gaussian distribution. Maybe you're not convinced that this thing actually is Gaussian because you see a few spikes here and there. So I've plotted this in what's known as a quantile plot, and it makes it a lot clearer that this should be Gaussian. So what you do is basically you take your data. In your x-axis, you have the, say, 5th percentile of your data, and in your y-axis, you have the 5th percentile of the data you're comparing it to. In your x-axis, you have the 10th percentile of your data. In your y-axis, you have the 10th percentile of the data you're comparing it to. And if these distributions are supposed to be the same, then when you plot it, it should be very close to the y equals x line, because that means the percentiles are matching up perfectly. And if you plot this against the Gaussian, so blue is n to a 3/5 plotted against the Gaussian, n is n to a 2/5 plotted against the Gaussian. In both cases, you see that the fluctuations are behaving pretty much exactly as Gaussian. So they're matching up almost perfectly on the dot. Okay? So this isn't the surprising result, though, right? Because heuristically, we can make sense of perturbing locally. Perturbing in just a coordinate, the matrix only feels it in a small range, so then it behaves as if it's just a matrix of that size. Sort of the strange part is when you drop in this all ones matrix. So why is dropping in the all ones matrix far more different in the band case? Well, again, let's look back to our picture. What happens when I drop in entries into all the coordinates of my band matrix? A lot of the entries that were just identically 0 now become active, right? These were the only entries that were surviving originally. But if I drop in my matrix of all ones, in some sense, the matrix is forced to realize that it's of full size. So if you're thinking of the bomb picture, the bombs are everywhere now. So your matrix is of full size. So what would you expect the fluctuations to be? It somehow can't avoid the fact that it knows it's an n by n matrix. And in the simulations, this is bearing out. It thinks that it's an n by n matrix. The scale of the fluctuations now is square root of n. I took my band matrix, I drop in this thing that makes it realize everything's there, and it fluctuates as an n by n matrix. This is still bizarre, though, because the entries of the matrix that are there are of scale 1 over square root 2 to the bn plus 1. Right? The scale of the perturbation and the scale of the matrix entry are different. But somehow, when I do this, it forces it to become like square root of n. So the same picture is here. Well, not the same. So I want to convince you that it's not the same. Again, people think that I'm always cheating. So full perturbation, square root of n. This is a distribution from the simulation. 2bn plus 1 matrix unit, and this is the distribution. Okay, so again, here's another quantile plot to show you that it's in pretty much perfect matching with the Gaussian distribution at the right scale. So then the question becomes the following. This is what I'm working on now, and hopefully this will be done at some point. Based on the heuristic, you would think that this should extend beyond just these special cases. So you should be able to say that localized perturbations result in fluctuations at the scale of the bandwidth. If you drop in any sort of perturbation where the eigenvectors are localized, it shouldn't make the matrix realize that it's that big. So things should only be fluctuating around the scale of the bandwidth. If you have the other extreme situation where you drop in something where the eigenvector is flat and it forces the matrix to realize that it's actually an n by n matrix, then the resulting fluctuations should be happening at the level of the dimension. The very interesting question, well, this is already hard enough, but a very interesting question that I'm considering is what happens in between? There should be some sort of crossover point. You don't necessarily need to drop in something that's full length to make this matrix realize that it's actually a full matrix, right? There should be some sort of crossover point where afterwards the matrix just goes, yeah, okay, I know I'm full size n. So this is something that we're looking into now. Another question that you might be interested in is, well, I did this for just the periodic case. A very natural question to ask yourself is, well, what's going on in the aperiodic case? I didn't discuss that at all. I have an idea for how this works, so it should just be a sum of a bunch of horrendous integral formulas, but we'll need to make sure that works out. And then the question of fluctuations there, that would be interesting as well, because the idea is, if you believe sort of the universality phenomenon, you expect these fluctuations to be identical, but somehow the fact that you're cutting off some entries at that scale should actually play a role. So it's not clear to me whether or not these fluctuations should still be like the periodic case, just because you've cut off a lot of the entries, there's no reason to think that this thing is still the same. Okay, and then of course this is the problem that I've asked a lot of people, which is how does this relate actually to the original square root n conjecture, right? So they were interested in local statistics and eigenvector localization, delocalization. In some sense, the conjecture, if proven, has some relationship to localization and delocalization, but of the eigenvectors of the thing that you're adding to it, right? So what about the eigenvectors of your original matrix? This is not at all clear to me, and I've asked a number of people, and it doesn't seem to be clear. And the last question, which is maybe a question that you're all wondering at this point, is where's the combinatorics? So that's sort of a question that I'd like to know, because based on our venerable triangle structure, we would expect that there is connections, right? So we know that for the Wigner model, there are these nice connections. In the band matrix model, if we knew these statistics, if we knew what the distribution of the largest eigenvalue was, its fluctuations around its extreme at bandwidths lower than 5.6, does that have a natural interpretation in terms of some sort of permutation statistic, right? Does this show up in a different way? And you would expect that there's some sort of combinatorial structure in the background that has the same distribution as a random band matrix. But again, it seems like we're quite far away from this. But if you want any of the actual details, I didn't go into the way I've proven these results, then feel free to come talk to me. But I think at this point, I think I should let you go and enjoy your evening.